All right. Let's do this. All right, quick reminders before we start. I'll try to remember this the first few lectures, first few weeks. I'll have the, what am I even trying to say here? Discord, thank you. I'll have the lecture question open on Discord on my phone. So if you have questions the old-fashioned way, or hit me up on Discord. And if you see me watching my phone during lecture, I'm not ignoring you all. That'd be incredibly rude. I'm looking for your questions, and I'll usually read them out loud when I'm answering a question from Discord. And I don't know if anybody cares about this, but I say it like the first lecture every time. When I'm presenting slides, you'll usually see me do this at the beginning of every lecture. I'll go to the course website, I'll click the slides, I'll download them, and open them right from that download. I'll do that. You'll see me do that at the beginning of every lecture, with, I don't know, maybe exceptions if I don't know. If there's no slides for that lecture, I guess you won't. Anyway, there's a few reasons I do this. One, I want to make sure, well, the main reason is that I want to make sure the slides that I'm presenting from are exactly the slides that you have available to you on your course, on the course website. As a student, I never liked when the slides I could download that were available were completely out of date. They weren't the same slides that were being presented. So I do that to, I don't know if I could pronounce that, Hi Ululu. That I want to make sure my slides I'm presenting from are exactly what you have. So I downloaded them like that. One, as a kind of show of faith, that's why I do it literally in front of you, just to show you that I am presenting from exactly byte for byte the same file that you have access to. But also to keep myself in check, sometimes I'll update slides at the last second and then I forget to upload them to the website. So just to verify for myself as well. Sometimes I'll download the slides, you'll see me do that, and then I'll be like, hey, this doesn't have my latest changes. Then I'll upload the latest slides real quick and then make sure they're in sync. So if you're ever wondering why I don't download the slides before lecture, that's why. Because I actually have them downloaded. I just did a 312 lecture 2 hours ago. I just downloaded them 2 hours ago. I'm downloading them again just for all those reasons. Okay, so today we're talking about, should I briefly? I'm not going to really talk about it today. I'm not going to talk about it at all. But homework 1 is released if you want to check out what's going on with that. I have it downloaded 3 times. This is the newest one, I think. I mean, I didn't change them today, so they're all the same. So today we're going to give an overview of the internet. And we're going to start kind of one of the themes, sort of unintentional, sort of intentional themes of the course, and that's dispelling magic. There's this tendency to think that the internet just works via pure magic, that everything just kind of works and it's really complex and hard to understand. We're going to dispel a lot of that. A lot of that's going to happen today with the internet itself, and then we're going to get into the stuff that we're actually going to build. So we're not building the internet in this course. I just want to give one lecture of background. This isn't stuff, the stuff today isn't stuff that you'll have to code. You won't have to code TCP or IP. We're not going to have to implement those protocols. We're going to start with HTTP. But I want to give some background, very quick, one lecture on how all of this stuff works. The internet itself, the internet protocol, and then TCP, transmission control protocol, which I always forget, but I know right now because, I just did it 2 hours ago. Let's do it. Let's start at the lowest level, the basic level, a local area network. This is what we're familiar with. Anybody who's ever used the internet is at least tangentially familiar with a local area network. This is the lowest level of a network, and we usually say the internet is a network of networks. This is the smallest form of that network. This is in our houses. We're going to have something that looks like this. At UB, it's still a LAN. We have these access points here that connect us to, and this, is that even an access point? Right there. We have these access points here that connect us to UB's LAN, and then there's all kinds of infrastructure, pretty large LAN of UB. But this is what we're familiar with. At home, we'll usually have an all-in-one router that is a router, a switch, and a wireless access point. Then that'll plug into our modem, and the modem plugs into the wall, which plugs into our ISP. So we're used to this. It's for a small network of machines. And we use I mean, not so much these days. We're going to use a lot of Wi-Fi these days, but we would use Ethernet cables here. We would plug an Ethernet cable into our router, and we plug an Ethernet cable into our desktop, and that's how we get internet. We have a lot of Wi-Fi at this point, but the Wi-Fi is really only at the LAN level, only right here, only from our laptops and phones to that thing right there, and that's it. Next level up is our ISP. This is the same idea. It's going to be cables plugged into routers, except we're at one level higher. We're going to be at the neighborhood level, at the even city level. The ISP is going to go around with these cables, and if you order ISP service, you call up Verizon, and you're like, hey, I need some internet in my house, and a new house that isn't already hooked up, they'll come out, they'll go up into the utility poles, plug into the pole, go over to your house, and literally plug your house into their network. This is the same idea as your LAN. You have cables routed through either utility poles or sometimes underground, but it's cables that are plugging in houses to the ISP's network. So we have one big network that's still routers, it's still cables, no Wi-Fi at this stage, but it's the same technology that's used in your house. It's routers and cables connecting that are speaking really ones and zeros. One level up from that are the tier ones. These are the ISPs of the ISPs. The ISP is going to talk to the tier one networks and purchase internet access from them, and then they're going to plug into the tier one network for internet access. And then the ISPs go into our neighborhoods and plug in our houses to these cables, to these networks. But the ISPs are going to get internet service from the tier ones. And these tier one networks are starting to be at the country level, at the continent level, and they're plugging cities in together. They're running huge cables, same idea, we're just plugging in routers, but huge cables that are spanning across cities. The distances are larger, the cables are larger, the bandwidth is massive, but it's the same idea, we're plugging in cities to each other. And these tier one networks usually have peering agreements with each other where they can use each other's networks effectively free of charge. That they just all kind of merge together into one massive network that are the tier one networks. This is what we call the backbone of the internet. If I were to point to any one thing and say that's the internet, it's going to be these tier one networks with their peering agreements. That is the internet, at least in my eyes. Other people can argue if they want, but they're wrong. This is the internet. The different access points have different IP addresses. I don't know if I'm prepared to answer that question. Because I don't think the access points themselves have IP addresses. Oh, actually, I think they do. Each access point itself would have a different IP address. But when an access point distributes IP addresses to us, I would assume that it's one big address pool that the IP address talks to the network controller and says, hey, I need an IP address, bless you. Then it gets issued one and then gives it out, but I am just guessing, I'm speculating there. I would be surprised if each access point had a range of IP addresses that it dishes out. But it might work that way. I'm not too familiar with that detail, that specific detail. So these tier ones have these peering agreements. So we have these massive networks that span countries, continents, connect cities, and they all agree to use each other's network free of charge. So it acts as one big network, which is, I already said this, but the backbone of the internet. And the ISPs talk to them and say, hey, I'll give you a bunch of money if I can plug into your network. And then different ISPs go into different neighborhoods and different cities and get us connected to those tier one networks. But what we really want is to be connected to those tier one networks, and that's what our ISP does for us. It gets from our house to the tier ones with their peering agreements so we can be connected to the rest of the world. So if everybody gets connected to these tier ones, and I say countries and continents, but they are across the entire globe, this big tier one peering network, we want to be connected to that, because once we're connected to that, we're connected to what we think of as the internet. It's this collection of tier one networks. And you might have heard of some of these companies, but unless you've looked into this before, you probably haven't heard of all of them. Level 3, L3 Communications is, I believe, still the largest Tier 1 network in the United States, and I'd be willing to bet that many of you haven't even heard of them. But they handle a lot of your internet traffic. As much as we like to blame our ISPs for things and talk about privacy with our ISPs, they can see all our packets, the Tier 1s kind of evade that conversation very cleverly. I don't know about cleverly, but they tend to evade that conversation. But they're probably handling more of your well, that's not true because the ISPs have to handle all of your traffic. But they handle a lot of your traffic. And we pay $90 a month for that. I mean, I have opinions on this. First of all, if you're spending $90 a month on your internet, you're paying too much, unless you need really high speeds. But it's for the internet. Like, can you live without the internet anymore? If they charge double that, I'd still pay $180 a month for internet. Like, come on, man. But yeah, I think they do charge more than they have to. Yeah, I think mine's $50 a month for Fios for 300. And $90, you gotta negotiate or something. See what the current rates are. It might, because Verizon, not to get too much on a tangent, but I noticed Verizon likes to just constantly increase my rate and not say anything about it. And then you got to see what the latest rates are and change your plan to one of the newest plans if you want to get that down. I was paying like $80 for 30/30, and I looked at the rates, and the current rates were $50 for 300. And I'm like, well, I want that one, obviously. Why didn't you just automatically put me there? And it's because they wanted my money. So anyway, a few of these, Verizon, that we were just talking about with Fios, some of these are Tier 1s and also ISPs, so the line can get a little blurred. Verizon has a large network. That's really what Verizon is. That's their cell network, their ISP. They have a huge network, and that's what they always brag about. And it's big enough to be considered a Tier 1 network, and they're part of the peering agreement, so they're a Tier 1 network. And they also go into some neighborhoods, certain neighborhoods, and say, hey, let's lay some cable and plug in some houses and make a little extra money over here. But anyway, these are the Tier 1 networks in the United States, and I very carefully only put American, United States Tier 1 networks. But we know, anybody who's used the internet, you can connect to Asia, you can connect to Europe, you can connect to Africa, you can connect to the entire globe. So how do we connect continents to each other? How does our message actually get across an ocean? That sounds hard. I've shared enough opinions, but I used to have Spectrum. I'll leave it at that. Back when it was called Time Warner. Not that I'm super happy with Verizon either. The ISP is really, I'm lucky enough to be in a spot where I have two options. Most people only have one, and they have a monopoly at that point. It's kind of crazy. Crossing the ocean with huge cables. Yes, exactly. This lecture was more fun like 5 years ago. A lot fewer people knew that, but now y'all know it. Y'all know that it's big-ass cables. Oops. I did this in the wrong order again. It's big-ass cables. We actually just take big cables. We take one end of it, plug it into one continent. We take this cable on a boat and unroll it, let it lay on the ocean floor, go to another continent, and plug it in on the other side. And bam, we have internet access across oceans. Big frickin' cables is the actual answer, which still boggles my mind to this day. It's still wild that's with all the technology we have and wireless technology, we have Wi-Fi and cell networks and satellites and stuff. Big cables is still the answer. At least as of today. It might not always be. We have Elon's working on Starlink that maybe we'll get satellites at some point. And there is satellite internet right now, but the satellites are in a higher orbit than Starlink, and the latency is just too much. It's too much latency to go all the way to space and then back down. It just takes too long, and nobody wants to deal with those ping times. But Starlink is going to be a lower orbit, which requires many, many times more satellites. And they've been launching lots of satellites to get Starlink up and running. That maybe someday these will be obsolete, but as of today, big cables. That's the answer. I got to rearrange these slides because I made this mistake in both lectures. But I mentioned that ISPs pay tier 1s for internet access. And I just very casually said, oh yeah, they just plug into the tier 1s. And these tier 1s have peering agreements, massive networks, huge amounts of bandwidth. And I said, oh yeah, they just plug into each other. But that's not nearly as simple as I'm making it sound. I'm way oversimplifying it. To plug these huge, massive networks into each other, we need something called internet exchanges, like this one here, with tons and tons and miles. I'm not even going to speculate a number, but lots of cables that need to be routed and plugged into each other into routers that are going to handle these massive exchanges of data at incredible amounts of bandwidth in high speeds, near the speed of light. That takes a lot. It's sometimes entire buildings. I don't think the entirety of 60 Hudson is an internet exchange. I don't know, it might be. I should probably just look that up since I use it in my slides every semester. But at least several floors of this building is an internet exchange, and these things are all over the world. Every city's got to have at least one internet exchange to be able to just handle all the massive amounts of cables that need to be plugged into routers to be able to communicate with each other to transfer data between huge, massive networks with millions of people connected to them. Lots and lots of cables. My point to all this, well, one of them is that the internet is not very magical. It's a very physical thing. If you're sending a message to somebody, say you want to send a message to somebody in Beijing. You want to go on WeChat and send them a message. That message flies through the air to, well, I don't know which access point, but one of these access points, I'm going to pick on this one, it's going to fly through the air. From this access point all the way to Beijing, you can follow a physical cable the entire way. It's going to be copper, it's going to be fiber, the material may change, but it will be a physical cable, no wireless technology at all, until it gets all the way to Beijing, and then that last like 20 feet to your friend's laptop. Then it's going to be wireless again, just for that last little bit of the connection. We don't use Wi-Fi much at all. Like, we use it because that's the only part we see is the Wi-Fi part. Everything else is physical cables. Even across an ocean, it's a physical cable, and then a bunch of routers plugging these cables into each other. Very, very physical thing. It's just a big mess of wires. We literally wrap the globe in a bunch of cables, whether those cables are fiber or copper, a bunch of cables. And that's what the internet is. It's just a big tangle of cables. Very, very low tech. Can't convince me the sharks don't know what they're doing. I used to put a video in these slides of a shark taking a bite out of one of the cables. And it just hurts its teeth. The cables are made for that, of course. What if the fiber optic cable on the ocean floor gets disconnected? It's, well, expensive to fix. But they go out there with a boat, send hooks or something, send stuff down there, grab the cable, bring it up to sea level, or not, yeah, I guess it would be sea level, but bring it up to the surface of the water, repair it on the boat, and then drop it, send it back down. It's a huge process to be able to fix them, but they do break, and they do have to be repaired. Sometimes they have to be replaced in big money investments. Worth it. I mean, to be able to have the internet be global, worth it. And that's why our internet is not quite $90, but $50, $60. Yeah, why is this so much brighter? Because I think I had this problem let me get to the next slide. I had this problem in the last lecture too. Some of my slides, I try to have like dark mode slides, but some of them are a little too bright. I might go one notch higher on the lights in the room. I'm going to try this out for another lecture or two, but so I don't burn all your eyes every once in a while. I think I'm going to have to go one notch higher in the lights. But the next notch higher is like the brightness of the sun. There's no in between with this one. All right. So why do we have all these cables? Why do we want to use the internet? Lots of reasons. Obviously, you know what you're using the internet for. But the main reason, is this even an opinion? I think this just is the main reason, is to connect to these things right here, data centers. It's not controversial, right? We don't have much peer-to-peer stuff on the internet right now. It's to connect to these data centers. When you go to an app in your browser and you go to some major app like YouTube, what you're doing is going through all those cables, going through all those routers, and then making it to one of these data centers owned by Google. This one picture is owned by Yahoo. This is one in Lockport, which is like 15 to 20 minutes away from here. You could drive to it, see it from the road, and take a look at it. It's I don't know. These things kind of spooky. These things scare me. The amount of computing power that's in these things is absolutely crazy. So this is multiple buildings. All these data centers are going to be a whole bunch of really big buildings that are packed to the brim with servers. Just lots and lots of computing power. And what gets spooky is when these things are, these days, running more and more AI. Like, these are like the nerve centers of what's going to take over the world eventually. It's, I don't know, it's wild how much power is in these things. So these are, if you haven't seen anything like this before, this is the inside of a server room, which is what these data centers are. They're just racks and racks and racks of servers. Each server is a separate computer. I'll use the word computer here. So this one, these are all individual machines. Machine's the better word. And there's just racks and racks and racks and racks and racks of them. When I use the word server in this class, I'm going to use it in a few different contexts. Today I'm saying server. I just said computer and device, but these are servers. When I say server, I'm talking about the hardware server. This is a server in the sense of hardware, which is just a computer, just like your laptop. Same technologies. They usually have more hard drive, more RAM. They're higher powered typically, but there's nothing special about them. It's the same technologies. It's still DDR RAM. It's just more of it. It's still usually Pentium processors, just bigger ones, more cores and stuff like that. But it's the same exact technology that you run. It's just one, more powerful. I said that. Two, shaped differently. They're just shaped flatter, so they can fit in these racks. So they can put racks and racks of them in a building like this. Doing this with laptops would be a pain in the butt to be able to do, or even desktops. Desktops just aren't shaped for this. So nothing magical there, just a different shape. And I forgot what 3 was. I swear I had 3 things on this list. Made to run 24/7. They're made to run 24/7, so cooling is important. They can run at 100% capacity 24/7, so just making sure that things are cooled. In these buildings, temperature control is the critical thing. Temperature and humidity, actually, are the critical factors of these buildings to be able to keep all these devices running 24/7 and hosting your apps. And we need all this power. So think of, going back to YouTube, thinking of what YouTube needs to run to manage all of the massive, I don't even know what the number is these days. Last time I checked, it was like 48 hours per minute. I'm sure that's horrendously outdated. But how much amount of video upload and video download, how much video they have to send, the amount of bandwidth, the amount of storage to store all of those videos, the amount of processing power to handle all of our requests and not crash too often. It's only been like twice to my knowledge, or in my memory, that I've been using YouTube and it was down. And then all the other websites got a ton of traffic because we all went to Twitter and Reddit to complain. But how much it takes, it literally takes buildings filled with machines running 24/7. A lot of computing power it takes to run an app. And it's very unassuming when you go to a major app in your browser. It doesn't look like much. Especially like Google search, just that little search bar, but how many machines, how many buildings full of devices it needs to run that thing, buildings full of servers. The other term I'm going to use server for is the one I'll use the rest of the semester. I'm not going to talk about server hardware, server hardware for the rest of the semester, but server software. That's what we're going to build in this course. You're going to write your own HTTP server. In software, you're going to run it on your laptop, test it on your laptop, but guess what? That's the same exact hardware as one of these things, just less powerful, of course, and you're going to have less users. You're going to have one user as you're testing, but the software that you write, if a lot of people want to use your app, you would, ring up, obviously not ring up, but you would go to AWS, upload your server software onto server hardware like this that AWS has that'll let you use for a price, and then you can run your app and have it distributed to millions of people if you have millions of people who want to use your app. So we're writing the server software, the same stuff that's running in these things. For enough money, you can have all this stuff. Okay, so how do we actually use these cables? We know our endpoints, all of our devices and the data centers. What happens in between? How do I just send a message to a data center? Is all the data in the server temporary? Yeah, it depends. I'll be so bold and say if they're doing their job, it's not temporary. And for most apps, unless it's specifically a feature of that app to keep your privacy and to delete things, then maybe they're actually deleting things. But like, YouTube's never going to delete a video that was uploaded. They shouldn't be. Do servers use a lot of helium drives or just normal hard drives? I have no idea. I've never heard of helium drives till just now, to be honest. But they tend to use cheap hard drives, which might help answer the question. They tend to use cheap hard drives because hard drives fail. It just happens. Even the highest end hard drives, they're gonna fail often. So they have a bunch of cheap hard drives, and when one fails, they swap it out and throw in another one. Just replace them. It's what the workers at those places are doing a lot of the time, is going out and swapping hard drives and swapping out entire boxes. Pull out a whole server. The server died. Pull it out, throw in a brand new one, and keep the system going. And everything's designed with enough redundancy to be able to handle those crashes, handle those hard drive failures. I was going to answer that previous question. Delete it. Yeah, you don't want to delete things. We're seeing this more so than ever today. This is definitely a tangent. But we're seeing a lot of AI these days. And AI is pretty dumb. It doesn't really do, how do I word this? It doesn't really do anything. AI is models of mathematics, statistics, and everything. And it's really useless, right? Until you feed it data. AI needs data. It needs training data sets to be able to learn and give the illusion of thinking. It needs the data. So if you have a whole bunch of data, you have every video that anybody's ever uploaded to YouTube, and you're trying to make AI that generates videos, you want all that data so you can write your model and stuff all of that data into the model and have it spit out something useful on the other end. That's the major reason why a lot of Google products are free, because they want our data, not because they're spying on us. People like to make it sound like, oh yeah, they want your data so they can knock on your door, and they do want it so they can target ads, but really they want it to train their AI. A lot of what their AI is doing is targeting ads, so yeah, I guess. But they want it to train their AI. They have all this search history. They have all these videos. They have all your driving behavior from using Google Maps. They take all that information and use it to train their AI. So that data is very valuable. So if they're deleting data, they're not doing their job, because their job is to get that data, train their AI, have the best AI because they have the most users to farm the most data to train the best AI. They start deleting data, and the competition is going to start catching up. So if they're doing their job right, they're not going to be deleting data. And they're not going to be sharing data. Like Facebook's not going to share data with Google and vice versa, because they want to both train the best AI. Among other reasons. Yes, I'm oversimplifying it and everything, but AI needs data is the big point I'm making. All right, so how do we use these cables? The Internet Protocol is the answer, of course. So the Internet needs a protocol, and that's the Internet Protocol. What else would we call it? I like it when things are named simple. It's a beautiful thing. So IP is how we actually use these cables. When we send something over the internet, it doesn't just get broadcasted across all these cables to everybody connected to the internet, to every single device connected to the internet. No, every single device, and this is a little bit oversimplification too, but every device on the internet has a unique IP address, and we send a message to a specific IP address, and the routers of the internet know how to get a message to that IP address to get it to that specific device. So we send a message to a specific device based on its IP address. So that big data center is going to have at least one IP address. It has many machines. Each device has a separate IP address, but it's got racks and racks and racks of devices. It can have more than one. But usually one access point into it. So we get that IP address, send it to that data center, and then do whatever we're doing on the internet. The Internet Protocol uses a packet switching algorithm, or I don't know if I can call it algorithm, but uses packet switching. So each message you send over the internet using IP has to be one small, what they call datagram. I like to call them packets. I mean, they're called packets too officially, but that's the word I prefer. But And these packets are fairly small. I want to say in the size of 10-ish K, like tens of K, tens of kilobytes. I forget the number. I should probably just look it up someday. And if you want to send something larger than that, you have to send it over multiple packets. So if I want to send a 4 gigabyte MP4, I'm going to split that into a lot of separate packets and send that over the internet, which is one of the really beautiful, elegant design decisions of the early internet that they just really nailed. They really got this right, is that the internet is packet switched, which means a router in the internet, there's no sense of like a connection between two people. A router in the internet has a queue of packets coming in, and it takes one packet at a time and sends it on its way. One packet at a time, send it on its way. So if somebody's uploading a massive video and has this huge queue of packets that are being sent to the router that the router's handling, and you want to say, like, hi to your friend. You have this one little packet that wants to get in there. You know what? It can get in right in the middle of that video upload, and that video upload doesn't prevent you from using the internet. And this is the beauty of packet switching with small packets, is that we can all share the cables. We can use them at the same time, and nobody's monopolizing all the bandwidth, which, of course, does happen sometimes. Sometimes the bandwidth is going to get capped out at a point, but it's much less of an issue as it would be if we didn't use packet switching. Yep. Yeah. Yeah. Yeah, so the question, if you're uploading something or downloading something, isn't the same processing power? And yeah, I don't know why. I don't know if I'm going to have a good answer for you. Why like the speeds are different sometimes, the upload and download speed. These days they do tend to be the same, which makes more sense. But yeah, sometimes I'd just be speculating if I were to give an answer. But my speculation is that it was kind of artificial. Like they would just limit your uploads for whatever reason unless you pay more. I'm speculating there. I could be completely off base there. But yeah, what you said makes sense to me too, that it's the same technology, it's the same cables, should be the same bandwidth, up or down. What's the cause of a packet loss? Ooh, good question. Okay. I gotta get through some of these. Some of those questions I'll answer just from the slides naturally, so I'll get to them. Packet switching, as opposed to connections, so like phones back, I don't even think it works like this anymore. Everything's voice over IP now. But earlier, like a long time ago, phones used to be connections. Like you would use up one connection, one cable, if you were to call somebody and there would be an actual connection that you're using and nobody else can use that connection at that same time. If you're on the phone, somebody calls you, they're getting a busy signal, nobody can use that. But that's not how the internet works. With packet switching, we can share the cables freely, and it really increases the overall bandwidth that we all get to enjoy. I like skipping that slide. There's two different types of IP. IPv4 used to be all we had, and this is 4 numbers ranging from 0 to 255, separated by periods, which is all complete crap. It's a complete illusion. It's actually just a 32-bit integer, unsigned integer. That's what IP addresses are for. And then for human readability, we like to split them into 4 smaller numbers, 4 8-bit numbers, and separate them by dots, just because it's easier for us to read, it's easier for us to see than one giant value from 0 to 4.3 billion. That's less human readable. But it's all an illusion. The computer just sees 32 bits, and that's it. 32 bits, that's what IPv4 addresses are. So since it's 32 bits, we get 2 to the 32 total possible addresses, which is that 4.3 billion, which sounds like a lot, but it really isn't. That's significantly less, much less than the total number of humans on the planet. So even if, not everybody has internet access, but most people at this point do, and it's just not enough IP addresses. Some of us have multiple IP addresses. I'm sure every one of us right now probably has at least 2 IP addresses that we need just to connect to the internet because we're spoiled like that. But we ran out of IP addresses. So we needed something new. We came up with IPv6 because screw IPv5. IPv6 has 128-bit addresses. So we have 2 to the 128 total number of addresses, which is that many, which is a big enough number that I'm not going to try to read it. We have a lot of addresses. And when I came up with IPv4, I like to think they looked at that 4.3 billion number and said, geez, that's so many. We're never going to need that many IP addresses. And now we know they were kind of naive. The internet took off, and it's a big deal these days. But at the risk of being naive, I'm going to say that's enough. I don't think we'll ever need more IP addresses than that. That's way more than we're ever going to possibly need. For some perspective, this number is larger than the total number of atoms in the known universe. So I think we're going to be good. I think we're going to be okay. And the internet these days uses IPv4 and IPv6 in conjunction with each other, so the routers of the internet have to be able to handle both types of IP addresses. So if you're sending an IP packet to some server or someone, you need their IP address. There's no other way around it. That's how the internet works, is by IP addresses. But throughout your life, you've probably never or at most had to worry about like 5 IP addresses ever in your life. And that might be being a little generous. We don't think in IP addresses, but we absolutely must use them to use the internet, and that's where DNS comes in. So we have domain names. You want to launch an app, you buy a domain name. You own that domain name, like google.com, buffalo.edu, and then you link that domain name. You create a DNS record to link that domain name to your IP address of the server where you're running your app. And then when somebody wants to visit your app, you tell them your domain name. They're going to type in their domain name in the browser. The browser is going to send a DNS request to a DNS server with a known IP address for a DNS server, send an IP packet requesting a DNS lookup for that domain name. The DNS server is going to respond with the IP address of the server you want to connect to, and then the browser sends a message, IP packets, to that IP address that we got from the DNS server. So it's all IP addresses. We need IP addresses, but we know the IP addresses for DNS. That's that's going to be pre-installed on your device or on your network or your router at home. Something in your home network, your LAN, is going to have a DNS IP address or multiple of them, and you can configure them if you ever are interested in it. And then an IP packet there to do the DNS lookup. So then we don't have to think about IP address. Oh, man, that one's bright, too. I'm not even looking at it, and I can tell it's bright. I'll suffer, too, here. So this is what IPv4 looks like. These are the IPv4 headers. So in these cables, everything's cables. It's copper, high voltage, low voltage. It's fiber, it's light, no light. It's Wi-Fi, it's wavelengths and signals. It's all just ones and zeros. That is the only thing we can communicate over the internet, is ones and zeros. So we have to make sense of these ones and zeros, and there's no magic here. We have a protocol. This is IPv4 headers, and this is going to specify what each one of those ones and zeros means. So, for example, we start with the version, and this is a screen, so I can't use my pointer this semester. So, for example, the version, it says the first 4 bits, so the first 4 most significant bits of the first byte is going to be the version. And since this will be an IPv4 header, that's going to be 0, 1, 0, 0 are going to be the first 4 bits that are sent, the first 4 ones and zeros that a router gets. So a router's sitting there waiting for IPv4 packets, or IP packets, and it reads the first 4 ones and zeros that come in, and it knows, okay, this is an IPv4 header. The next 4 bits are going to be the IHL. Next byte is going to be the type of service. The next 2 bytes are going to be the total length. And all the way down to the most important piece of information, the destination address that the router is going to read to figure out where this thing's supposed to go. But there's no magic here. We look at this protocol. Whoever's writing software that goes in your operating system that sends packets, whoever is going to follow this and create packets that follow this sequencing of bits, sequencing of ones and zeros, And anybody writing code for a router, and now I can get off that page, writing code for a router is going to do the same thing. They're going to read the documentation on what the IPv4 and IPv6 protocols are and code to expect the ones and zeros coming in to have those certain meanings. But we're just artificially assigning meaning to the ones and zeros by following the same protocol. And if everybody follows the same protocol and follows them correctly, we can have effective communication over the internet and through the routers of the internet. Each router has a very simple job. A router is connected to multiple other routers. I guess some of them could just be connected to one, I suppose. But a router is going to be connected to multiple other routers in the internet. Router is going to get a packet from one router or from an end user. And its job is to figure out what the next hop is for that packet. And that's it. So they're going to have something called a routing table. They're going to look up in their routing table based on the destination IP address what the next router is that should handle that. So it's going to get a packet. It's going to look at the destination IP address, and usually only a certain number of most significant bits of it. It's going to look at a prefix of it. So it's only going to read a few bytes in most cases, and then send that packet off to one of the routers that it's connected to, and done. Its job is done. That's what the routers of the internet do. I'm oversimplifying a little bit. There's some more details there. For example, the routers have to know how to update their routing tables as other routers go offline and come online and things like that. And they have things like time to live. If a packet gets stuck in an infinite loop, a router's got to detect that and then not send it again and just cut their losses and say that packet's done. So a few other things. But for the most part, that's their job. Very simple, and we like it that way. A router gets a packet, checks part of the IP, sends that packet on its way, goes to the next packet. We like it that way because it's fast. These routers are made for speed. They're not made for reliability. They're not made for any processing. They're just made to be fast. And they are fast. They're quite fast. We like the internet. We can send a message across the entire planet in less than a second. It's pretty awesome. There's some problems with this, though, and that's where TCP is going to come into play. The problem is, since that's all the routers do, well, there's a lot missing there. Who's guaranteeing that our packets are getting to their destination? No one. Not the routers of the internet, at least. The internet is an unreliable network. You cannot guarantee that your packets are going to get there, and this is a question in chat. We do have dropped packets. It's a reality of the internet. Packets will be dropped. It happens. It happens often. We're going to lose data. We're going to send internet packets, and they're not going to get to their destination. This will happen. And also, some internet packets won't get there in order. They won't get there in the right order. So, for example, I'm sending a whole bunch of packets. I'm sending 200 packets through the internet. And one router is sending packets to another router, but then it updates its routing table. It finds a faster path and starts sending packets over this way instead. Now, these packets that go this way arrive before the packets that went this way, and now all these IP packets are getting in out of order. They're getting all mixed up, and we're missing a couple of them. Everything's all jumbled up, and it's, difficult to communicate like that. It's going to be hard to get our packets. So this is where TCP comes in. So IP doesn't make a connection like the old days of phone calls. It doesn't do that. It just sends packets. It's packet switched, and the packets just kind of go into the internet and hopefully make it to the other side in any order. TCP is going to fix this and make add some reliability to the internet by creating an actual connection, kind of pretending that we have a connection. And this is up to software at this point. The routers are running software too, but I consider them more hardware. This happens at each device. Every single one of our devices has to implement TCP. I guess they have to implement IP too, so that's a bad example. But we have to handle TCP at the device level. So with TCP, we're going to make a connection before we do any communication. This is done through a three-way handshake. The client is going to send a SYN pack with a random number M to the server that they want to connect to through using an IP packet. They're going to send this IP packet. That IP packet doesn't, nothing happens. There's a timeout, and then we resend it and keep resending until we get this one through. So if this one gets dropped, we have timeouts and resends to be able to handle that. The server is going to get this packet. It's going to read M. It's going to add 1 to it, a very complex protocol here. Add 1 to it and respond with an ACK packet with M plus 1. Seems very simple, but there's a lot going on here to be able to get that to happen. So what happens with this, what's happening is the server is showing the client that it speaks TCP. It knew where in the sequence of ones and zeros to find the value M. It extracted that, interpreted it as an integer. It added 1 to it, so just a very minimal amount of computation, and then correctly assembled an ACK packet and sent that ACK packet in the right format with M plus 1. So the client, after it gets that ACK, it's saying, wow, okay, this server does actually know what TCP is, and it did implement the protocol, at least the first 2 parts of the three-way handshake. It at least understood how to do that, so it gains confidence that it can actually establish a TCP connection and that the server is going to know what to do with that. The server would like the same confidence, so it's going to send its own random value n and get its own n plus 1 back. And after that three-way handshake, we have an established TCP connection. With this TCP connection, the client is going to send, usually along with that third leg of the three-way handshake, it's going to send some information, some meta information about the transmission that's about to happen. And then included in that is, hey, I'm about to send you some stuff. It's going to take 200 IP packets. I'm going to send you 200 IP packets. And when I send you those packets, I'm going to give every single packet a sequence number. And when you get all these packets, they might come in out of order, but rearrange them. I'm going to give each one of them a number 0 to 199. You're going to reassemble them all and then be able to smash together this original message that I was sending you. So we handle the out-of-order issue by giving sequence numbers to each packet, and we're going to handle the dropped packets issue because when the server gets this message, it says, hey, I'm going to send you 200 packets, and it's reassembling them 0 through 199, and it says, hey, I'm missing, and it looks and says, I'm missing packet 133. Well, packet 133 must have been dropped. So now, instead of saying, hey, can you resend that? I didn't quite, I got the message, but it's all corrupt and stuff. Instead, we're going to say, hey, can you retransmit 133 for me? And we send one packet instead of the entire message again. We send that one packet that was dropped. And then once all the packets are at the server, it can reassemble the original message. And then at that point, it's sent to our software. And then it's in our hands at that point. All the IP headers are stripped. All the TCP headers are stripped. Both those protocols did their job. And we have the entire original message that was intended to be sent to our code, and then we get to start implementing HTTP at that point. For what it's worth, TCP is what adds the idea of port numbers. So with IP, you send a message to a specific device, but that's really not enough. We have multiple processes on our device that all want to use the internet. Each one gets a different port number, which no magic again, just a number. So we say, send this packet to this IP address. IP cares about the IP address. TCP cares about the port number, and then it gets routed to the correct process. TCP and IP in our code, we're just going to use a library. It's going to do everything for us. Then we start with HTTP. If you want to know more about networking, TCP, IP, UDP, Modern Networking Concepts is the course for you. It'll go in way more depth. I'm doing one lecture. They do an entire semester on a lot of the same ideas and go way, way deeper into all of these topics. And with all that, I'm going the wrong way. With all that, we do have our first lecture.